NDS for all. So whereas the growth you get from, say, the Plouniker-Rouge lemmas is exponential here. You get a factor like k to the n. So this is important. This is stronger than exponential, obviously. And we will also need some definitions. As I said another definition. As I said last time, some people, Sanders included, prefer not to go all the way to generalized progressions. No, they can, because you can get them from what I'm about to state. They just feel that the following is a bit more elegant. So as centered, the E is optional because that's just the split between the UK and the US. So Sanders does not use an either. So it's a set such that there exists a convex symmetric set. So what do I mean by convex? I just mean that it's its own reflection. So there exists a convex set that is symmetric around the origin and a homomorphism such that the image of the intersection of the integer lattice with the convex set under the homomorphism gives you P. And it is not hard to show that. So P contains a progression of a generalized arithmetic progression of dimension of d and size at least d minus d log d. I should also say that Sanders just works with this, and that's enough for him, because even if this is not proper, this already has this already grows just by 2 to the d, or a constant to the power d. However, I feel it's nicer to make clear what proper means in this context. So we will call this progression proper if phi restricted to ZD intersection Q is injected. So this is just a matter of language. In fact, we have essentially seen this already in that when we did Minkowski's second theorem, which of course we did not prove, but we saw how to use it. Very well. All right. And remember that Minkowski's second theorem did not assume we were working with a box. It was valid for any symmetric convex set. So this is precisely a sort of assumption that is enough for it. Very well. So as I said, Sanders splits the main theorem into two parts. So there's theorem 1a. Let G be an abelian group. A subset of G finite A plus A at most a constant times A. Then what? Then A is contained in the union of, so let me put it this way. Of how many copies? At most, e to the log k to the fourth copies of a set S, which happens to be symmetric, and S itself is not too large, and most importantly, S has relative polynomial growth of order of log k to the fourth. So A is covered, just as before. The ultimate result comes when A is covered by few copies of an arithmetic progression or a convex progression. So here, A is covered not yet by a convex progression, but by relatively few copies of a set of relative polynomial growths of moderate order that is not much larger than A. So I say relative, well, relative is just relative to A, but I said moderate growth rather than small growth or moderate size. What do I mean? Well, we have e to the log k to the fourth here. That's much better than e to the k, say, obviously, or e to the square root of k, or e to the k to the epsilon, or what have you, but it's still not quite optimal. So first of all, let me tell you that this has been improved already once. So this was improved by Konyagen, who will be visiting us in late November. So he went from 4 to 3, both here and here. That's not trivial. That's already good, 1/3 of the way up to 1, which is where we want to get. So optimal will be if 3 were made into 1. So if we had 1, that would be so this would be, of course, k to the O of 1. So it's allowed to have O of here. But probably do have an O of here. So yes, let me be safe. So what you really want, what would be optimal, would be k to a power here and log k here, because then you would have you would have a result that is from which you can deduce the assumption, and that would be really the polynomial conjecture. All right. So this is the first half. This we will do in full. And this is the part that should be optimized. And some people, say Ben Raymond, feel very strongly that this is an important problem, to improve this in this way. So this is the so-called polynomial Freiman-Ruggia conjecture. All right, what would be theorem 1b? Also Sanders, though this is, I would say, halfway Sanders, halfway Green-Ruggia, and as we will later see, over Z, you can really do it with Chang. So let me be an abelian group, SG finite of polynomial growth of order D. Then there exists a proper centered, let me write centered in the American way, convex progression P. And for general groups, we would also have an affine subgroup H and G. Of course, in Z there are no finite subgroups except for zeros, so we don't really need this if G is Z, such that S minus S is containing P plus H, the dimension of P. So this is not quite optimal. Optimal would be O of D, but we're almost there. And P plus H very well. Что?
Ограничений на размер подгруппы никаких. Просто на конечные.
Да, это может быть конечно. We will work with a finite group, but this sort of thing works for infinite groups as well. Well, we're interested in Z, which is infinite, but we reduce it to Z modulo PZ, so we could work just with finite groups, but it is fairly general. No?
You see, we do not have any power on the size of this finite subgroup. Only maybe on this.
Oh, but yes, it's all that we need. The sum to be not much larger than S. I do not know whether we can bound H individually in a better way, but I don't think it's very important because it's anyhow. And for us, H will not exist anyhow. Over Z, H is. Well, and of course, the fact that H is finite is implied by the fact that it's finitely bounded way. All right. So as I said, this is almost optimal. So almost, because there's still a log square D. Very well. Yes. So here I would just like to note that it's not hard to see. It's at most 2D to the. That's very easy if P is proper. That's only slightly harder if P is not assumed to be proper. All right. So how shall we go about this, and where is page 3? Important question. Here's page 3. So as I was saying, why did I even write this? Yes, because I was about to, well, imagine I did not erase that. Just to be complete, I was about to write, let G be abelian, finite. I'm just going to join the two statements. So then A is contained in, well, just to write in words what I wrote before in symbols, in O of log K for O of 1, though this can be 3, copies of P plus H. So I'm just putting together the two theorems, where P is a proper centered convex progression. Very well. All right, what we had seen before was Kronecker-Rouge. So this is exponential, of course. So how are we going to obtain polynomial growth? So-called relative polynomial growth. Can you see the chalk clearly or not? My drawing technique is not what it was one day be. All right, very well. So first try. So we recall Rouge's covering lemma, and it's covering lemmas that will provide us with a transition from exponential to polynomial growth. So there exists a t of size almost 2a minus a plus a divided by a, and this of course is at most k to the 4th times a by Kronecker-Rouge, or just Kronecker for short. I think Kronecker gave the first proof and Rouge gave a nicer proof, such that 2a minus a is contained 2 in t plus. No. So we're applying Rouge's covering lemma to the two sets 2a minus a and a. And so because 2a minus a plus a is not much larger than a, you can cover 2a minus a by few copies of a minus a. And now how is this useful? Well, you see you can get a chain reaction going on here. So we apply this recursively n minus 1 times, and we get that n minus 1 a plus a minus a is contained in n minus 1t plus a minus a. And what now? Well, since G is abelian, mind you, Rouge's covering lemma works even in non-abelian groups. But here we use the fact that G is abelian. How? Well, to bound this, it looks as if these were going to grow exponentially, but it doesn't really. Because we have that the size of n minus 1t, well, you see the order does not matter. So we're just distributing n minus 1 tokens among t individuals. Things are going to be repeated n minus 1 times. It's just that which element of t gets which parts, that's the question. So this is just t plus n minus 2, which is at most n to the t. Hence, na, which is at most, of course, na minus a, is at most n to the t minus a. K to the fourth is large. So this shows that actually that the exponential growth that you get from Ruja always implies, surprisingly, polynomial growth. But it's polynomial growth to a very high order, to the point that it's useless, or almost useless. It's n to the the order is k to the fourth. Whereas we are aiming overall at, well, ideally, growth of the order of log k, but in practice, growth of the order log k to a power. Okay, so we will give a second try. So we saw last time that there was not just Ruja's covering lemma, but also Chang's covering lemma. So, and using Chang's covering lemma, or rather a small variation, we can prove, as was said in an email, the class will now start at 2:30. All right. And there was a discussion of topics to be presented at the seminar at 2. But very well. So, in fact, what happens here is that if we can prove sub-exponential growth, which we don't get right away from Plunike's lemma, but which we will have to prove for moderate sub-exponential growth for at least, in fact, you don't need to show sub-exponential growth overall, just for at least one moderate n. I will make clear what that means. Implies polynomial growth. How? Well, there's a variant of Chang's covering lemma. I will sketch the proof, but I will leave it mostly as an exercise because it's essentially it's a variation, a small variation of what we saw last time. So it says that if you have two subsets, AS, of an abelian group G, 0 containing A, if you need, such that NA plus S is less than C to the NS for some n. So, by the way, Sanders states it with C equals 2, which is all that you need. And, of course, it looks much more special, but we can prove it for C. He gives also a slightly stronger conclusion, but it does not matter. Then, there exists a T in A, T less than 2n, such that A is contained in the span of T as S minus S. I will just remind you of what the span is. The span is just what you get by adding and subtracting different distinct elements of a set. So it's, if you wish, a span with coefficients bounded by 1, integer coefficients. So you see, it's almost a special case of the version of Ruja's covering lemma we saw last time, the assumptions look different, but that just means that the proof will be shorter, because we do not need to use Plunike's lemma here. We're pretty much given what we deduced last time from Plunike's lemma, namely something of this sort. And we just need it for one particular n, not for all n. Someday there will be self-drying blackboards, but that's not the day yet. We are not there yet.
We bit confused with the bound. No, I'm sorry, it was 5 minutes ago, but the bound on the top of the lower desk. Where do you get it from? And
so, wait.
The top of the lower desk.
Yes. Yes, the scar.
Yes, and why it is better than n to the power.
All right. It's very simple. As I say, I'm using the fact that G is abelian. So you have t columns, and you are counting the number of tuples of t integers that add up to n. All right, but that is just a number of ways of partitioning n into t parts. So it's, well, you add, yeah, all right, that's pretty much it. Because you're adding some counters in there, and then you're choosing where to put the counters, that's all. And then, you can give the explanation in Russian to everybody as well.
Я просто пишу, поэтому я не
понимаю.
Это не аналитическая оценка, это комбинаторная оценка.
Да, это комбинаторная, да.
Потому что
нет,
просто...
And this is just, this is very, very simple. This is just write it down.
Просто потому что ты берешь и считаешь, что...
But this is important, because it's... Yes, no, thank you for making that point, because here we're using the fact that we are in an abelian group, but it's not a trivial step. Of course, it's very simple combinatorics, but you have to get into that frame of mind.
Why is this much better than just the stupid bound?
Because the stupid bound would be exponential, just like the bound we started with. Yes, I mean, in some range, the stupid bound will be better, but eventually this bound will be better. So for large n, this is better. But it's a bit of a miracle that you can get any sort of polynomial bound from, well, basically any exponential bound there, or well, from small doubling. Anyhow, so then you recall the chunk covering lemma from last time. I will give the proof as an exercise with some hints, because it's really just
Yeah. You see, you began to explain with span t.
yes.
And then
Span of t is the set of all combinations of the form EI does. Yeah. Yes, it's just that. All right. So this will be an exercise. It's like last time without the last step. So without Plunike, because we're already given what we use Plunike for. I I write Kronecker instead of Kronecker-Rouget just because it's shorter. So just to remind you, it was an inductive reasoning starting with V0 equal to S. Here we have a maximal BI free part. And then we define the psi to be a subset of Ri of size C, Bi plus 1 rather than 2C like last time. And then this is the loop. So it's written almost like a computer program. So just flesh it out. It's a good exercise. But the corollary would be then, what do you obtain from this variation on chunks covering lemma? So someday there will be self-wiping blackboards and also noise-free chalk, but this is the human condition and we will have to deal with it. So if we have a subset of an abelian group, a symmetric subset such that, let's find it, 3n plus 1 x is more than c to the n. This is just for convenience. Of course, since c is arbitrary, I could just write n here. I could write n here. So we just need the growth to be sub-exponential for some n. And then if c is bounded by a constant and then it's not too large, we will get a beautiful conclusion. So we'll get then x has relative polynomial growth of order of Cn. So in practice, in Sanders' proof, what you aim for is equal 2, in fact, but c equal 3 would be just as good. Very well, and you need this to happen for just for one n, but of an n that is not too large. Very well. So here. All right. So it should be small, of course. This is what we aim for. All right, so how are we going to get sub-exponential growth? So the strategy, the basic strategy will be the following. So to get sub-exponential growth for some small n. So the following strategy clearly works for some n, but not necessarily a small one. And really the fight will be to get sub-exponential growth for some n. So aim at a result of the following sort. If doubling is small, then for any m, there exists a t in G, the usual conditions, such that t, so it's clear what the omega notation means, right? It's the other side from O. It's at least, well, I could, if you prefer, I can write it this way. So do you prefer big O, small, big O and omega notation, or do you prefer this sort of notation? No preference.
In Russian, big O is
more common. And then do you do omega then for the others? Did you omega is this. So which means bigger than a constant times. A positive constant, of course. And if I have little things here, this just means that the constant depends on this. So synonymous. MT containing for x. Very well, how to use this? Well, you see, once you have a result of this form, of course you want a good dependence here, but once you have a result of this sort, where MT is containing for x, what can you do? Well, you combine this with Pluneke, you see? Because we're going to have that this is contained in 4Lx. This by Pluneke is at most K4Lx, which, excuse me, by, let me use omega just to, no, wait. So 1 over omega is O. So this is O of mk K4L All right, so what are we going to do here? We are going to set, let me see, what did I write here? We're going to set n equal to ml, very well. I'm growing very slowly. We sell, how slowly? Just enough that of m of 1 there is less than L, but at the same time m goes to infinity. We get 3n plus 1 is less than little o of k. And this, of course, is going to be smaller than 2 to the n for n large enough. So you see right away that we do get from a result of this kind that you do get sub-exponential growth thanks to from sub-exponential growth you get polynomial growth. The one question is, well, first of all, we have to show something of that sort, and the other question is, well, how large is large enough? we don't want it to be very large. And well, how do we prove this? There were proofs before. I mean, if you take as a starting point what we did last time, then you can deduce from that versions of this result. But they are not going to give you, it's going to be circular. They are not going to give you anything stronger at the end. If you use forms of the Feynman-Rouget's theorem, then you can obtain things of this sort. But that's not what we're aiming for. And it turns out that one can get a pretty good result of this form, and that's what Sanders did, without using Fourier analysis, in fact. It's very tempting, and maybe there's a way to get an even better result using Fourier analysis. But I think he was the first to give a result of this kind without using Fourier analysis, though he is using a very important analytic lemma by Crout and Sisask. Very well. So this is what we're going to talk about here. So the Crout-Sisask inequality. Sometimes called a lemma. I think it should be at least a proposition. So let us just call it an inequality. We will spend most of the rest of the class here. So we will be using some non-trivial inequalities. So Marcinkiewicz-Zygmunt. Very well. So let P be at least true. Let x1 be things that are LP measurable with respect to some measure. And these are independent random variables. Then, and we assume that the expected value of the sum is 0. So this is only this is a standard inequality, but I will sketch the proof briefly, very briefly. Nevertheless, so, by the way, is everybody familiar with LP norms? Yes? Yes. Sorry? It's basically, I was about to say, so the hint to the proof will be that you just prove it using Hintgen. And I was going to hint how to prove Hintgen. So let me see. So first of all, note that this is tight. So this is tight, at least for xi of variance 0 and mean 1. And then, well, things converge to the normal, and if things converge to the normal well enough, then this is an exact result. In general, it's not necessarily tight for all variables, but it's a pretty good inequality. So how do you prove it? So sketch of proof. So you reduce it using standard techniques, which I will not go into. And let me just say what goes into this. First of all, it's very easy to see that you can assume that these variables are real valued. And more subtly, symmetrization, and one might say, I'm not sure it's a standard name, but quantization. So you want to make, you see Hintgen, at least in the standard forms, takes in symmetric variables that take two values. So this is more general, but it's basically, I would say, cosmetic. Though, I mean, Marcinkiewicz and Zygmunt really applied it in full generality in analysis. So this reduces to Hintgen's inequality. So Hintgen's inequality is this, well, the same, with Well, x1, xn independent with just a very simple distribution. We just take two values, each of them. And then the conclusion is just the same as above. I will just write it in full. It's that the L norm of P, rather the expected. No, it's exactly that. It's the L norm is going to be O of square root of P. And here comes the same expression as here, which I can write out in full. Now, actually the proof of hinging is very easy. In both of these cases, the issue is to come up with the inequality, not so much to prove it. So to write things out explicitly, this is just ai squared to the p over 2 I. So what would be the sketch of the proof here? Well, you can reduce Hinging's inequality. You can reduce this to p an even integer by interpolation. Again, a standard technique. And then what you do is you actually just do it. I mean, you raise these things to the power 2m, you write out a big sum, some variables just vanish, poof, and then only the squares survive, and that's what you get. Expand. Non-square terms die. Collect terms. All right. But, so the proof here is just, you just do it, and the proof here is, well, you just ask your analyst friend to teach you basic techniques. That's what I would do. Well, really techniques in probability, and then you get this inequality. But it's rather powerful. Then the great merit was that of Crout and Cisask, who managed to prove some very nice things using this. I will follow the account in Crout Laba Cisask, who managed to make the statement of the statement, the proof of Crout Cisask cleaner and more general by splitting it into two halves. It's possible that just one half of it could be continued in other ways to give other results. This is a possibility explored in Crout Cisask Laba. But the hopes that might give better results for this problem haven't been realized yet. But I think this is time to make a short break, and after the break we will do the Crout-Cisask theorem. Let me just, I was told that not everything was clear, so let me just go over what I just did. So at first I just stated what we mean to prove. The first, still not optimized half, what people should work on, and then the second, almost optimal half. And we're going to prove the first half at least. Then I said that, well, so the first half is about covering your set with small doubling, with x plus x smaller than k times x, by something that has polynomial growth. So what I first gave was, well, how on earth are we going to get polynomial growth? So at first I showed that using the Rouget covering lemma, you can get polynomial growth from small doubling quite easily. Well, that was a tricky combinatorial thing, right? Unfortunately, the order is too big to be useful. It's k to the fourth. But that already shows you that covering lemmas, simple covering lemmas, are quite powerful. Then I showed how Chang's covering lemma allows you to get polynomial growth if you have sub-exponential growth. Already a big step. So what we should aim for is getting sub-exponential growth for some small n, small h, meaning a power of log. So how are we going to get sub-exponential growth? So here I showed the basic argument, not yet done formally. We will redo this more formally with precise constants and parameters. But this shows you that if you can find a big T containing X, such that even m times T is still in 4x, does not leave 4x, then you're basically done. You get sub-exponential growth. And now the rest of the talk essentially will be about how to find a big T such that m times T is containing 4x. And this will take some analysis, and this is the basic idea will be the Cauchy-Zizek inequality, which I haven't yet stated, but which I will state right now. And we will prove it using Marcinkiewicz-Zygmunt, which, yes, is essentially a generalized version of Hinchin. So where were we? Yes, I should have done this while everybody was drinking coffee. Or while I was explaining everything yet again. But since there's not much water left in the sponge, at least we will not need to dry anything. So, any questions so far? Is everything clear? What is not clear? Tell me while I finish wiping the board. So you have about half a minute. I haven't yet formulated it. I'm about to formulate it. This is what I'm wiping the board for. If you wish, I will let Marcinkiewicz-Zygmunt stay. Oh, but I erased the conclusion of Marcinkiewicz-Zygmunt, so never mind. I think at least that I erased the conclusion. Yes. All right. So what is the Cauchy-Zizek inequality? I will actually delay that a little bit because I'm going to follow the formulation in Cauchy-Zizek-Laba. They split the statement into two halves. So just a bit of notation. Let me go right away. So lemma A. So there are other interesting things in this paper, but this is basically a reformulation of just Cauchy-Zizek. So let P then there exists, no, what have I written here? All right, so we have a probability space, we have these measurable functions with LP norm bounded by 1, though that's just a convention. And we let G be a linear combination of these things over here. And so what I claim is that there is a K which is not too big. Can people actually read this or not? No problems. I'm not yet a master of the wiping thingy, but maybe when I leave St. Petersburg I will be. There exists a K that is not too big, and a K tuple, sigma 1 up to sigma K, where sigma I is an integer from 1 up to n, such that we'll put a little star on the conclusion just for further reference. The difference between G, well, scaled down, this is the L1 norm, and the average. In other words, so this linear combination of possibly very many f's is going to be expressible. I think there's a little thing here. Yes, and I believe, yes, if I'm right, what is meant by this. So lambda O is just lambda divided by a modulus. Well, in the case of 0, it would be just 0. So this is telling me that, and this is in the LP norm, this is telling me that I will always be able to find as a fairly small set of f's such that the difference between G and just this much shorter, poorer linear combination is small. If the f's were orthogonal and if p were 2, this would just be the most basic thing in Fourier analysis, or in, well, vector calculus really, where you just say, well, I'm going to pick up the biggest components. So you see, if this were Fourier analysis, and p were equal to 2, then this would just be a linear combination of characters. I mean, this would just be the Fourier decomposition of f, and I would just be saying that it's enough to pick 1 over epsilon squared characters, the biggest ones, in order to approximate G well by that shorter sum. And you just do what I just did. You pick the biggest characters. Here it is more general. We don't have any sort of orthogonality as a requirement within the FIs. And more importantly, here we're working with the LP norm, which is can be much more sensitive if we set P to be higher.
And it can be infinity, for example.
Actually, I'm not sure about infinity, but it can be as large as you want. There will be a little problem with infinity in that you will not get any bound on K. But it can be pretty large. All right. In fact, something stronger is true, something stronger that we will use. Little star holds with probability greater than, say, 0.99 if sigma 1, sigma k are just picked at random. That, of course, with a weight distribution with probability, so this way, so that lambda sigma 1 up to lambda sigma k divided by the L2 norm to the k, so that, of course, bigger coefficients, quote-unquote coefficients, lambda, are more likely to be picked. So it's funny, I don't know whether taking just the largest lambdas would work, but taking the largest lambdas more probably does work. And we will actually need that there are many ways to do this. So what is the proof? So as I said, yes.
What is the norm of lambda? Is this the Euclidean norm or L1?
Here's the L1 norm. Here's the L1 norm. This is one. Do people prefer?
And you see, we're talking about probability.
Sorry.
Do we suppose that lambda is positive? Because if you write probability,
yes.
You need them to be positive.
What do you mean?
Lambda sigma 1.
Why would you need them to be positive? Oh, I'm sorry. Thank you. Little circle here.
Maybe so you take
Yeah, so this is lambda, little circle, is lambda divided by its absolute value. And if any lambda happen to be 0, we just pick it to be 0 probability. Wait, am I telling the truth there? No, I may be lying. Let me see. Do we need absolute values or nice ratios? I think, no, I think we need absolute values there, not little o's. Let me just double check. Goodness gracious, this is in cross Labasisas. But this is take a big absolute value here. Then we're happy. All right. All right. So do you want me to draw my ones this way or that way? Do sevens have a mustache in Russia or not? This one?
Yes.
Okay, if 7 has a mustache, then 1 can be like this. Very good. I will not necessarily remember, but... So, well, you pick h at random from one of these things, just with probability. With probability again, proportional to the sizes. Yes. By the way, in the applications to Kruth-Sisesk, everything will be real, but it's good to give the complex statements just because this does have interesting consequences in complex analysis. Well, in Fourier analysis. Then, the expected value of h is, of course, just lambda I divided by lambda 1 fga is g over lambda 1. So call this G0. So let H1 be independent copies of H, of course random variables, just like H itself. We wish to show that H1 plus K for K large enough. And here we apply Marcinkiewicz. All right. Here I have just restated the basic strategy, which is to pick these things at random, and usually these things will work out. So by Marcinkiewicz-Zygmunt, we have that the expected value of the difference between this average and our random G0, well, our expected value, G0, d mu. So this is just an easy application. Just go and apply it. Here the expected value 1k so here p over 2 and here the parenthesis is closed. Very well. Now we just have to simplify this expression now. This was the hardest bit of analysis, but now comes an easier analysis. So we do have that it's not really a but, and really. Oh, so we do have what? That this integral well, we can use a very special case of Hölder here, which is to Hölder as the usually applied case of Cauchy-Bunyakovsky is to Cauchy-Bunyakovsky. I remember to say Cauchy-Bunyakovsky. But Hölder is just Hölder, there's no Russian analog. So we apply it with I equals to p over 2, so we get that this is 1k of, here we have the sum and this is equal very well. At the same time, you just have the triangle inequality. So this is equal to FIP for some Fi. We don't care which one. And is at most 2 by the assumption, which is just a matter of normalization, that Fi has at most 1, is at most 1 in LP norm. So where were we? And where did the expected value go? Well, the expected value is sort of irrelevant because this is true whatever G0 is. So the expected value of all of that this side this is at most a constant to p over 2. The constant is basically 2. But all right, what do we do now? What do we do now? We just choose C small, say C equal to 0.01, since we are aiming at 0.99, fairly arbitrary. And C prime about C over epsilon, so it will still be a constant, and we pick k equal to C prime P epsilon squared. Then what do we have? Yes. Is everybody lost? Hope not. Yes. So we were here. We applied Marcinkiewicz-Zygmunt, and I want to show that this is basically 1, or well, a constant to the p, but it's going to just become a constant here. And that's what I did. And it's not very heavy analysis. It's basically Hölder. Hölder and the triangle inequality. You do it and you're done. You get that basically only this survives. So now we still have some work to do. So you're going to pick k big enough, but of the promised size, it's at most a constant times p over epsilon squared. Then the expression in the bound here just becomes c times epsilon p. And so now a Markov's inequality very well. We get that just from this very easily. The expression inside. So maybe Markov would be upset because it is a trivial inequality, but that's what people call it. This is going to be at most epsilon, this probability at least 1 minus c, which is what we wanted. So that's it. I know analysis, but we got done. Now, let me just say that this lemma A could be applied in different ways. As I said, it's particularly elegant if you apply it to Fourier analysis. Though this is not what we will actually do, I will state it on the board just because it makes the meaning of the lemma clear. It's pretty much what I stated before, only now it's more general. So it's not trivial because now P is arbitrary. And this is really the contribution in Kreutzig-Sklaba, in that, if you have G finite, then G decomposes its Fourier expansion very well. So what is he telling you? This tells you that you can approximate a function very well by a short chunk of its Fourier expansion, not just in the L2 norm, that would be trivial, but actually in LP norm. And this was apparently not known before. But we will actually work, we will not use this. So I think Ross-Lavancisas were trying to do better than Sanders. He's a paper that comes after Sanders, but didn't quite. I do not know whether there's a way to get a polynomial from Enrique conjecture using this sort of reasoning. There is still going to be explored here, because we haven't got the polynomial from Enrique conjecture yet. All right, so let us prove the Crotz-Cisas lemma, which is in physical space, so to speak. So Fourier space and physical space are just fancy words for using the Fourier transform and not using the Fourier transform. So, in so-called physical space, that is, without using the Fourier transform, we get theorem. I mean, people call it a lemma, but I think it's a theorem. Let's call it the Crotz-Cisas inequality. Some notation. Mu s is just the characteristic function of S normalized, so that the L1 norm is 1. And by rho x, I will mean the right regular representation. That means this will just be a function for x in G. This will be a function from G to G, such that the function evaluated at G is just going to be f of x plus d. So, in other words, rho x of f, rho x just displaces f. It does not change any of its norms, obviously. All right. So what is a Crotz-Cisas inequality? So let P be greater than 2, eta in O of 1, G a group, F will be a function on G in LP, that is itself LP norm is finite. ST are finite subsets of G with the small doubling condition, or precisely S plus T is smaller than LT. Then the set big X of all x, little x, such that the displacement of f convolution mu s is close to f convolution mu s. So the displacement of f convolution mu s is very close to the convolution itself. So this barely changes when I displace it by x, even in LP norm, which is stronger, more sensitive in this context than L2 norm. So I claim that the set of all x's, all little x's, that barely shift this convolution is large. and satisfies either way. But this just follows from the definition. All right. Yes.
Who is tau the power of eta in the bound?
No, it's 2. It's a very poorly drawn 2. There are no taus. Yes, -2. Very well. All right. How are we going to prove this? So first of all, I mean, why? The statement is quite simple. Could it be simpler? No. I mean, if I had no convolution here, then this would be clearly false. Functions do tend to change a lot. I mean, they don't change in LP norm, but they tend to get away from themselves when you shift them around. But the point is that if you have already smoothed, so to speak, f by convolving it with μs, then and you have a set T that does not change much if it's shifted by s, then there are quite a lot of x that will change this convolution, this smooth thing, by very little. Morally, then, the statement makes sense a posteriori, but it's really very strong because this set is so big. This just means that if you have smoothed something by an s, then there are many things that don't change it by very much when you shift it by that.
So, some heuristic points of view, we should think about such sets, yes, that with doubling properties as
Yes.
functions. Yes.
Sorry?
So
We should think of them as?
Of such sets with small doubling.
Yes.
As of smooth functions. Because
It's something that is smoothing the function, so to speak. Yes, I would say, morally speaking. Smoothing in the sense of making. So f can be something very wild, but if you smooth it, if you convolve it with μs, s is a set, in practice it will not be very small, then you're smoothing it to some extent. Very well. So proof. Let G be convolution, Sviorka. I like the name Sviorka. Then by definition, G is 1 over S, S in S, Fs, where Fs is rho minus S, F. That is, Fs is just the shift of x by minus s. By lemma A, Pitka. Much better. It's a lemma with 3 m's. By lemma A, well, of course, that just fixing, we have to fix the normalization, but we can assume without loss of generality in applying lemma A that Fp is 1, you just divide it by the LP norm, we get, let me put a little star here, j 1 up to k, fzj p less than or equal epsilon fp. You do get this for many tuples, for 99% of all tuples. So let L be the set of such tuples. the idea, we're actually almost done. I mean, the main element is lemma A. The idea will just be now that because of the small doubling condition, I mean, I'm not even using it several times or using Kronecker-Ruja, I'm just raising it to the case power. What happens is that so S plus T is not much bigger than S. It's like mice in a box. So some elements of L will be sent to other elements of L when displaced by some elements of T. So let us do this formally. So, I mean, basically it's clear that if you have got almost all elements, almost all tuples of this form, and then you start to displace them by elements of T, but by displacing them you cannot go into a much bigger set. S plus T is barely larger than it. You're going to be only barely bigger set of tuples, then there are going to be plenty of coincidences. In fact, you can probably do this as an exercise, but let me do this formally. So in full, B for diagonal, L plus diagonal is in S plus T to the K, and so L plus delta LK SK is at most 1 over 0.99 L to the K times big L. Thus, if we take the inner product of the two convolutions, which is just the L2 norm squared of this, just by this fact, this is, well, by Koshiv-Jakowski, this is delta squared L LK. Now, the rest is just a very simple argument, which you can probably do yourselves, which you can do yourself. I think you can still do this and go to the main part. Since this is never bigger than L, there are at least 0.9 times delta squared over L to the K pairs Z, Y in delta cross delta such that 1 minus L star 1 L Z minus Y is bigger than 0. And so there are at least 0.99 delta over L, that is 0.99 T over L elements T of T minus T, such that T can be expressed. The idea is that when you get a displacement that sends something in L, sends a valid tuple to another valid tuple, you're in luck because you're essentially expressing the displacement, and it turns out most displacements can be expressed in this way, or very many can be expressed in this way, as a difference between two valid L tuples. And that means that you will be able to get hold of the displacement using the triangle inequality for some set Y in delta. Very well, but that means we're done. By little star and the triangle inequality. You see, you have G minus 1K, just little star, for Yj, but you also have, then when you take the displacement here, Well, as I said before, LP norms are invariant under displacement, so I can just... But what happens here is that this becomes f yj plus t, but it's just zj. And since zj is also a valid tuple, then you also have that this is bounded by epsilon fp. So by star and by star. And so now, by the triangle, here we apply the triangle inequality. We get that rho t g minus g is bounded in L2 norm by 2 epsilon fp. So we just set epsilon equal to 8 over 2. And that's it. Very well. So we just have enough time to see how Sanders used Kreutzig.
One small question. Is the group G assumed to be
Abelian?
Is this group G assumed to be countable?
Good question. Assume it to be countable, but why? Did we make did we have to assume that at some point?
Otherwise,
Yeah,
you have
it's.
to put some measure on it.
I know. Well, you would have to specify the measure and so on. I think since our sets are finite, we're working with the counting measure anyhow. Yeah, it's an interesting question how to generalize these things to non-finite sets when you put measures on them and so on, but let us not go there, especially not today. So if you put p equals 2, would you actually recover traditional results like the ones we saw last time? So the idea really is how to use the fact that we now know the Kreutzig lemma, which we have just finished proving, for general p. Okay, I'm going to hate the sound. Oh, I see. It's this chalk. So proposition, Sanders. And perhaps I will just have time for this proposition, but this will be the main thing, because with this proposition, using the argument I sketched about an hour ago, you do get the results I claimed at the beginning. So this gives you the missing step. So S symmetric. S plus S of small doubling, S also doubles with T, and then equal to 1. Then there exists an X in G, symmetric, So the proof is quite simple. We just have enough time to do it. Just let me say that this will imply prop 1a. So I don't have time for. I really wish we had a bit more time, but just let me say that the second half of proposition 1, you can find the proof for every group in Sanders' notes, but if you want just to do it for Z, in fact, the arguments I gave last time, if you rearrange them, the ones with Bohr sets and Chang's lemma, which we did not prove, they do give you proposition 1b. So let me just, since we will not have time, prop 1b, use Chang's lemma. Not the covering lemma, but the other one. The one with the span. Or C Sanders / Green Ruja for a general group. But the point is that we have seen the essential ideas. So let us just now go to the proof, which is really the core of Sanders' contribution. The proof of that statement. So what are we going to do? We put f equal to 1 s plus s and apply Cauchy-esque. We get x such that x is large and the displacement of the function, well, convolution of mu s with f is close to the non-displaced function for every little x and big X. So by the triangle inequality, and it is this that will allow us to put mt in for s. By the triangle inequality, the same thing will be true, but, well, with a bound that is m times in size, and not just for little x in x, but for little x in mx. So by Hölder, this time the general case of Hölder, not the very special case we saw last time, you do get that the inner product here, it's because we can apply Hölder and not just Cauchy-Bunyakovsky, that we can use large p and not just p equal to 2. So I'm essentially just writing down what Hölder is. Here p prime is just the conjugate exponent, that is the number such that 1 over p plus 1 over p prime is 1. So for p equals 2, p prime would be 2, but for p much larger, p prime would be closer to 1. Now what? Now we just have to compute all the quantities here. Now, 1 s plus s star, so here we're using the fact that s is minus s. So this is 1 s plus s, comma, u star, and here comes a very clever but completely trivial thing. This is 1. Why? This is just because the support of mu s convolved with itself is equal. In fact, it's enough for this to be contained in this plus s. You see, this essentially means that this is just the same. This is just the same as the L1 norm of this, or rather, it's just equal to the sum of the values of this, because every non-zero value of this lands on a 1 here. And here comes some even easier computations. This is K1p S1p. New SP prime is equal to, let me just get this, S minus 1p. You can do this yourselves. And so I'm just writing down what you get, because this is 1 and we have just computed what these two things are, and the s's cancel. You get that this minus 1 that's it. We just pick an appropriate value of p, which turns out to be fairly high, not enormous, but log k. And so as I said, the important thing is that p does not need to be 2. We can set p higher. P is log k, so p just kills k completely. Eta is set to 1 over 10m, so this also gets killed. So all of this becomes less than 1/2. But if this is less than 1/2, this means that this is positive. And so, well, I should write it in full. This is positive, meaning that what I just wrote. X is contained in S minus 3S. That is, X is contained in 4S. And that's what we wanted to prove. I'm afraid I will not have time to do the rest, but I have given you all the important steps. Because what remains from this proposition to deduce from this, you see, this is really the proposition we wanted from the beginning. And I give you the basic argument. So once we have got mx containing 4s, then I already give you the basic argument of how this implies sub-exponential growth. So you do that, taking care of setting the constants correctly. That's really an exercise. So slightly unfair, given that, of course, it is because we're out of time, but deduce Sanders's theorem 1a from this. Well, it's not so unfair. I already gave you all the ideas. And I think this will have to be it for today. And I think this is a good point at which to close the chapter on Freiman-Ruja. As I said, well, you know, in nature it's not closed yet because we haven't yet got the polynomial Freiman-Ruja conjecture. People have to get a better version of theorem 1a. Whoever does that will be, well, I'm sure it will be published in a nice place. So this is an open challenge for you all. I wanted to say a few more things and give a bit more detail, but I hope to do that in the notes. So yes. So thank you very much for having sent me the notes for last time. If somebody wants to send me the notes for today, typed up, so they can use it as a first version, I will thank him also. And then I hope to be able to put together complete notes for Freiman-Ruja in English. But the notes in Russian for the first talk have been online for a while now, and I hope that they are now in a highly visible place, unlike what was the case before. All right. And I think we can pass on to the next topic next time.